Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to go over the 5 types of reactions. And so these are reactions that you should know, the various groups or categorizations or types of reactions, so that you can identify them and be able to predict products or reactants. So if you know what to look for in order to identify the types of reactions, then you'll be able to either identify the products if you're given the reactants, or be able to predict the reactants from the products. So let's get into this. So the first one on the list is the synthesis or combustion, or I'm sorry, combination reaction. So synthesis reactions and combination reactions are the same type. They go by the same name. And the name speaks for itself. So when you're synthesizing, you're putting things together. So things that are apart, you're putting together. You're combining things. So in this reaction, this reaction is two things are combining into one thing. That's what you're looking for. That's what you see. And so what you're looking for is more reactants than products. So if you start out with more reactants and you end up with products that are less than the reactants that you started with, like if you have less products than the reactants you started with, then that would be an indication that it is a combination or synthesis reaction. So here's a couple examples here. So here I have x plus y equals xy. So these two separate entities, they could be elements. Usually they're going to be elements. So you have two elements react together to form a compound. It doesn't have to be two elements, but usually they are. So basically, you could have two compounds or one element and a compound. But the idea is that they are coming together. They're separate. They're coming together to form a compound. So here in this example, I have carbon, which is an element, and I have oxygen, which is also an element. But notice that is O2 and not O, because it's one of those diatomic elements that you need to know. So diatomic elements or molecular elements, you need to know those. So these two are going to combine and form one thing, carbon dioxide. So here I have two things, and they combine to form one thing. So that's your synthesis or combination reaction. So that's one category that you should be familiar with. The second one is the opposite of synthesis or combination reactions. They're decomposition reactions. So decomposition brings to mind something that is decomposing. It's breaking apart into its elements, right? So a decomposing animal, right? The tissue and the proteins and the muscle are all together when the animal is alive, but when it dies, it starts to decompose, and the elements, the parts kind of degrade and separate into each other. So it's the same idea here. So instead of combining, you start with one thing, XY, a compound, and it divides into two separate things or more than two. It could be, again, separating into two elements, or it could be two compounds, or it could be a compound and an element. And so here in this example, I have some calcium carbonate. Calcium carbonate will naturally break down into calcium oxide here plus carbon dioxide. So here we have two compounds. Here we only have one. So what to look for a decomposition reaction is you're looking for more products than reactants you started with. So here I have one reactant, but I end up with two products. So that's your decomposition reaction. Okay, so synthesis, combination, decomposition, these are opposites of each other. What about combustion reactions? This can be tricky for a lot of students. So I'm going to go over this and try to hit the highlights on this one. So combustion reaction, that is a burning reaction. And so this is almost always a hydrocarbon. Not always. I got an example down here. I'll talk about that in a moment. But it's almost always some sort of hydrocarbon. What is a hydrocarbon? A hydrocarbon, as the name indicates, hydrocarbon, hydro referring to hydrogen, carbon obviously referring to, you guessed it, carbon. So a hydrocarbon is something that has hydrogen and carbon in it. So it's that sort of compound. So when you burn a hydrocarbon, you always get certain products from it. So here's an example. So you got some sort of hydrocarbon, it's always in the presence of oxygen. So this is key to a burning or combustion reaction. Something is reacting with oxygen. So as soon as you see oxygen as a reactant in your reaction, it is a combustion reaction. No matter what this other thing is, it could be a hydrocarbon or it could not be a hydrocarbon. But if you are reacting with it in the presence of oxygen, and that oxygen is one of your reactants, then it is a combustion reaction. So for hydrocarbons, if you are burning a hydrocarbon, meaning it's reacting with oxygen, then the products are always going to be carbon dioxide and water. That is assuming a complete combustion. If it's an incomplete combustion, meaning that you don't have enough oxygen to react completely with the hydrocarbon to produce these two, then what's going to happen is you'll get other things forming like soot, carbon monoxide, other things. So here we're assuming a complete combustion reaction. So under those conditions where you have enough oxygen, you have plenty of oxygen, then the products are always going to be carbon dioxide and water. So here's an example of a hydrocarbon, CH4. That's methane. So CH4, carbon and hydrogen, that's your hydrocarbon. That's going to burn in the presence of oxygen. So you notice we have a coefficient 2. And then here it's going to give us carbon dioxide and water. And we have a 2 coefficient in front of the water. So this is a good example of a hydrocarbon being reacting in the presence of oxygen. And so this is a combustion reaction. Here's an example of a combustion reaction where you don't have a hydrocarbon. So instead of a hydrocarbon, you have phosphorus. And notice here, phosphorus is in the form P4. So remember, that's one of your molecular elements. So phosphorus is often in this form, P4 form. Okay, so here we have phosphorus reacting with oxygen. So again, as soon as you see oxygen as a reactant, it is a combustion reaction. And so you'll notice here it gives you P4O10. Now the thing about these sorts of reactions where you have oxygen reacting with, say, a non-hydrocarbon, you can get multiple kinds of products from this sort of reaction. And so it's hard. It would be hard to tell what your product would be unless you were told what it is, or unless your teacher gave you some more information about the reaction. Okay. So notice one thing I want to say is that this is not a synthesis reaction. You might look at this and say, "Oh, look, I have 2 reactants, but I'm ending with 1 product." So yes, this is a synthesis reaction in the sense that you're combining 2 things in one, but you should be more specific. This is, yes, a synthesis reaction, but it is specifically one that has oxygen reacting with something else. So the better answer would be a combustion reaction. So make sure that if you see 2 things reacting together to form one thing, right, before you say synthesis, double check to make sure that one of the reactants is not oxygen. If one of the reactants is oxygen, then this is a combustion reaction, and that is the answer you should be putting down. Okay, so to recap, what are we looking for? We're looking for something that reacts with oxygen. That's the key for identifying a combustion reaction. If it is a hydrocarbon reacting with oxygen, then the products are always carbon dioxide and water, assuming it's a complete combustion. And then if it is something other than a hydrocarbon, then there's going to be a lot of possible products. And I don't think you'd be expected to know those unless, of course, your teacher or professor gave you more information or told you what to expect or what he or she expects. Okay, so I went through 3. I'm going to pause the video and we're going to come back and I'll hit the other 2 in just a moment. Okay, and we're back. So here are the other 2 categories of reactions. So the 4th one is single replacement or single displacement reactions. You could see them called either way. Sometimes they're called single replacement reactions or single displacement reactions, but they refer to the same type of reaction. And this is where you are swapping one element or ion for another element or ion in a compound. And the ion could be a single monoatomic ion or it could be a polyatomic ion. So in the example here, so you have some sort of ion or element that's by itself. You have a compound, and the element kicks off one of these. So remember that when you're writing a compound, if it's ionic, which usually a lot of these will be ionic compounds, the metal is written first, or the positive ion is written first, to be more general. And then you have a negative ion. So positive ion, negative ion, cation, anion. And so your element, depending on what this element is, if it's a metal, then it's going to kick off the cation, which is probably going to be another metal. And then you'll end up with a different compound with A and C in it. And then you've got the other element left over. In this case, it would be a metal, or this could be a nonmetal. In this case, it's going to kick off the nonmetal part of your ionic substance. So that'll be kicked off. And then what will be left would be, B and A. So instead of AC, you have BA. And remember, I'm saying BA because B is first because that's the positive ion. So positive ion is always written first. So this would be BA. And then you'd have C left over here. So here's a couple of examples. Here's one with a metal. So I have a metal element by itself, and here I have an ionic compound. So this metal is going to replace that one. So it's going to kick that off. And so then it's going to form aluminum with the nitrate. So it's going to pair up with the nitrate, kick the lead out. And then, so then I'll have my aluminum nitrate new compound, and then I'll have the new element, the metal, by itself. And so that's an example of where you have a metal as the reactant here. If you have a nonmetal by itself, so here you have the element by itself, it's a nonmetal. So then this nonmetal will kick off that nonmetal and replace it or displace it, right? So then what you'll end up with is KBr instead of Ki. So the metal goes with this new nonmetal. And then iodine, is now by itself. So it's being replaced or displaced by the other non-metal. And so both of these are examples of a single displacement or single replacement reaction. And as you can see, the reason it's called a single replacement or single displacement is because you have one element replacing singly one other element in a compound. And so the analogy I like to use is ballroom dancing. So anyone who's been involved in ballroom dancing or swing dancing, there's two partners, usually a man and a woman, right? So you're dancing together, the man and woman are dancing together, and you've got a guy who's stag, right? And he comes to the couple as they're dancing and he's like, "May I cut in?" And so, of course, if the woman allows it or if the man allows it, right? So it's up to the man, I think, or it's up to the woman. I don't know these days. So then they would change partners. So the man would replace the other man and dance with the woman in the dance, right? So that would be a single replacement or single displacement reaction. And so, and the thing you got to keep in mind here is that what you're looking for here is you're starting off with an element and a compound as your reactants. And then the products are still going to be an element and a compound, but they're going to be different ones because you replaced one of the species in the compound with something else. And so the thing to keep in mind here is in order to predict whether this reaction is going to happen or not, or to predict what products you're going to get, if you get any, is you need what is called an activity series. And the activity series is basically a list of elements in order of reactivity or strength in the reaction, or what oxidation of reactions or something along those lines. So then you'll have a list, And usually the way the list is put is that the higher on the list, the stronger you are. So if you are looking at metals, right, if you want to know if aluminum is going to replace your lead, then you would see, is aluminum higher on this activity series? If so, aluminum would kick off lead. So in my ballroom analogy, maybe the guy who's cutting in is bigger and stronger, maybe more handsome, and so the girl is attracted to him more, and then so he cuts in and he's able to, like, push the other guy out and dance with the girl, right? So that would be kind of analogous to the activity series. But I'll cover activity series in my next video, but I just want to point it out or talk about that as something you need in order to predict whether you'll have a reaction or not. Finally, the double replacement or displacement reaction. This is where you don't have one species being replaced. You don't have one ion or atom being replaced in a compound. They're both being replaced. And so in this case, you need the swapping of two elements or ions. And again, these ions could be polyatomic ions, right? So when I talk about ion, it could be polyatomic or monoatomic. Same thing here. This could be a polyatomic or monoatomic ion. And so you're swapping both of them. And so in the example here, you have AB as a compound and you have CD as a compound. And these are usually going to be ionic compounds. And then what's going to happen is these partners switch. So you have A and B together, and you have C and D together. And remember, if these are ionic substances, the first one is positive, the second is negative. So first you have the positive, then you have the negative. First you have the positive, then you have the negative here. So you can't put positive and positive together. They don't like each other. So negative and negative can't go together. They don't like each other, right? So opposites attract, right? So in the ballroom dancing, opposites attract, right? So here, so A is positive, that's going to be attracted to the other negative. So we already have it here in that negative. So in this case, it'll go to the other negative. So they'll swap these two together. And then we have the positive here, and the B is negative. So those are going to go together. So then the A and D go together. A is positive, so that's written first. So A and D go together, form a compound. And then we have B and C, the inner ones, go together. And C is written first because that's the positive ion, because we have it written first here. And B is second because it's second here. It's a negative ion, so it'll be CB. So the thing to remember is, in this case, when you're predicting your products, you're predicting which ones come together. If you're given the reactants and they're ionic substances, it's always the inner ions go together. So these two inner ones, the ones that are closest to the plus sign, those are the inner ones. Those go together to form one compound, one possible product. And then A, B, A, D come together, the outside ones, the ones farthest from the plus sign, come together, and those are going to form the other product. So these are the two possible products you can have. And so here's an example. So here you have silver nitrate reacting with potassium chloride. And if this was the only one I was given, I would say, okay, my possible products are the inner ions go together, so the potassium and the nitrate, so KNO3. And so I get my KNO3 here. And then my other would be the outside ion. So silver and chloride would go together, and I get my AgCl here. And so these would be my possible products that I could predict that would occur. Now, when I'm predicting products, I need to use what is called a solubility chart or something along those lines, where I would predict whether or not these are a precipitate or not, right? So these are usually going to be aqueous, but then I want to predict, are these going to be soluble or insoluble in water? If they're both soluble in water, then they're both aqueous, and that would be no reaction, because aqueous means these are dissolved in water. So if I have a beaker of silver nitrate dissolved in water, and I have a beaker of calcium potassium chloride dissolved in water, and they're separate beakers. If I put them in a single beaker, like here, let's pretend this is a single beaker, then if they're aqueous here, that means they're just floating around in water. Nothing's happened. So between here and here, they're floating in water. So here we have them floating in water, and here we would have them floating in water if they're aqueous. That means nothing's really changed. They're always floating in water. So, but if I get a solid forms, if one of these is insoluble, that means a solid forms, they come together, they form a compound, and then I do have a reaction. So in order to figure this out, I need to look at my solubility chart, I need to look at solubility rules, and then determine if I have a precipitate. Or another thing is if I form a liquid, right? If one of these, if it's an acid-base neutralization reaction, here, if AB is an acid and CD is a base, then I could end up with aqueous and liquid water. Or if it's a gas production, right? Maybe it's a gas formation reaction, right? I might form a gas here, so that would be a reaction. So those are some of the things to look for in your replacement reaction. But generally speaking, what do you want to look for? You want to look for reactants that have two compounds, and then the products are also two compounds, but they're different compounds. And again, these are usually going to be ionic. So if you want to identify a reaction as a double displacement or replacement reaction, you would be looking for something that looks like this. Two compounds here, and then two different compounds here. Okay, so I hope this is helpful. If you enjoyed this video, then please hit that like button right there. And also subscribe to my channel, hit this notification button right up there, and also put a comment down in the comment section. Let me know what you think. And but before you go, I'm going to give you a flow chart that will be helpful. So just one moment, and I'll give you that flow chart. Okay, and so here is the flow chart that I told you about. So take a look at this. So the first thing you want to do when you're trying to figure out what type of reaction you have is look at your reaction. And then ask the question, are there more reactants than products? If yes, there are more reactants than products, then you've got a synthesis reaction. So A plus B gives you AB. And again, here's the example. Oxygen plus carbon dioxide forms carbon trioxide here. So 2 into 1. If the answer is no, the reactants are not more than the products, well, then the question is, are there more products than reactants? So if the question is yes, then you've got a decomposition reaction. So your AB goes into A and B, breaks apart into A and B. And so again, we have the example, calcium carbonate breaks down into calcium oxide and carbon dioxide. So the 1 goes into 2. Okay, so what if that's a no? Like so not only are the reactants not more than products, or the products not more than reactants, then the next question, then that eliminates decomposition and synthesis, right? So the next question would be, is one of your reactants oxygen? If one of your reactants is oxygen, if that's a yes, then now you know you have a combustion reaction. So remember, combustion reactions are reactions where one of your reactants is oxygen. So again, you could have a hydrocarbon CXHY reacting with oxygen. If you have a hydrocarbon, then your products must be water and carbon dioxide. And here again is the example I gave you. And here's the other example where it's not a hydrocarbon. So the thing to keep in mind is, if you have a hydrocarbon, always water and carbon dioxide are your products. If it's not a hydrocarbon, then it'll be hard to tell what your products are going to be, because it could be a few different products. Okay, so then if one of your reactants is not oxygen, then the next question is there an element that's by itself that it swaps places with an element in the compound? If the answer is yes, then you've got a single replacement or single displacement reaction. And here's the information given that. So you have A plus BC gives you AC plus B, and here's our reaction. So here you have one thing swapping for another. So if you have a cation swaps cations for cations, or anions for anions if you got an ionic substance. Okay, so then if it's no, if you don't have an element by itself that's swapping places with another element in a compound, then the question is, do you have cations and anions switching between two compounds? If that's the case, then you definitely have a double displacement or double replacement reaction where the inside ions are going to come together and the outside ions come together. So here's a nice flow chart that you can use that may be helpful for you to identify what kind of reaction you have. And then, of course, if you know what kind of reaction you have, then you can figure out how to identify the reactants if you're given products, or products if you're given reactants. So I hope, again, you enjoyed this video. If this is a helpful flow chart, if all of this was helpful, or if any of this was helpful, please like my video, hit that like button right there, hit the notification button right up there for my YouTube video channel, so that way you can be notified by any videos I put out. Please like my channel, subscribe to my channel, put a comment down in the comment section, let me know what you think, or or any questions you have. I would love to hear from you. Thanks for joining me. Have a great day.